All right, in this section we're going to learn about planar graphs, and a graph that is planar is one that can be drawn so that no edges cross. So it doesn't mean that it is only drawn in that way. Like here we have a graph where certainly we could see some edges crossing. But if we just sort of redraw these edges, let's say, so this is the bipartite graph, the K-2-3. And I could draw this edge here, and I'll draw this edge here, and I'll draw this edge here. So those are all the edges going from the vertex A to the vertices on the other side. And now we need the vertices from B going to the vertices on the other side. So, you know, drawing from B to E is pretty easy. But then I need to get from B to C and B to D. There's nothing that says that edges have to be straight lines. So I'll just draw this edge this way and this edge this way. There we go. That's planar. Now, once we have a planar graph, if we've drawn it so that the edges don't cross, we can define what we call a face. So a face of a planar graph is basically like the pieces, you know, where these edges as borders. So the definition says a maximal section of a plane such that any 2 points within the section may be connected by a curve that does not cross an edge. But it just means that, you know, these edges, they form like the boundaries of some faces. And if we imagine, if we cut along these lines of the edges, we could kind of cut it into these whole pieces. So this graph has 3 faces if we include the outer face. So here's a face, right? Here's a face, and then the outer face there. Euler's formula of a graph. Euler has a role in really all areas of mathematics. So Euler's formula in graph theory says that if we have a connected planar graph that has V vertices, E edges, and F faces, then it is always the case that V minus E plus F is equal to 2. So in the graph above, there were 5 vertices, 6 edges, and 3 faces. So V minus E plus F is 5 minus 6 plus 3, or negative 1 plus 3, or 2. And there we go. That result is illustrated there. To see one way to use Euler's formula, I mean, certainly if we have a connected planar graph, you know, like the one we just drew up there, we can verify, we could see that it's true. In this next theorem, we're going to use that to help us show that a graph is non-planar. So the graph there that we just worked with, that was K-2-3, the complete bipartite graph with 2 vertices on one set and 3 vertices in another. We're going to look at K-3-3 and show that it is non-planar. So K-3-3, the complete bipartite graph with 3 vertices in both sets. So this looks like this. So we're going to do this by contradiction. Let's suppose that K-3-3 is planar. All right. So we know that we know the number of vertices and edges in K-3-3. Now there are 6 vertices and 9 edges. So if it's planar, we can figure out how many faces it would have. Now Euler's equation, Euler's formula looks like this. So 6 minus 9 plus f equals 2, and this means that f is equal to 5. So if it's planar, it has 5 faces, all right? Now, the complete, any bipartite graph, right, we split it up into 2 groups of vertices. I think of the top group and the bottom group. So I'm going to just label these groups. I'll have group A of vertices and group B of vertices. So let's let A and B be the disjoint sets of vertices. So A is the vertices on top here, B will be the vertices on the bottom. And let's think about what it takes to make a face, right? In order to have a face, I'm going to scroll up to the example that we just looked at. But if I look at the first face here, right, in order to make that face had to be bordered by these edges that make a cycle, right? So making, having a face means that we have the existence of some kind of cycle here. So to make a cycle that doesn't have any repeating edges, in this graph, K33, supposing we start at A, like if we start in the top with the top vertex. Our cycle has to have a certain form. Remember, there are only edges that go in between from A to B and B to A. There are no edges that go from A to A or from B to B. So a cycle would have to have this form. Let's see, I'm going to just sort of draw it out to see how long this cycle would have to be at a minimum. So let's say we start here. I have to go to B, right? Now I can't go back, I can't finish the cycle now because I can't just go back on the edge I traversed. So that means I have to go back up to A, and I can't finish the cycle now because I can't get from, within 2 vertices in A. So I have to go back to B, and now this is the first time, I don't have to, but this will be the first time, the shortest length cycle that I can make. So it would be from A, B, A, B, A. So that's the form it would have to take. And this is at least. It could be longer, but it is at least that length. So that means each cycle in K33 has length at least 4. 1, 2, 3, 4. Yes. And that means, if we imagine this, that somehow we could draw it so that it's planar, right, so that the edges don't cross, that would mean that the sum of the edges of all of the faces, right, each face is defined by some cycle, right, of whatever length, but each of those cycles is at length at least 4. So that means that the sum of the edges of all the faces is at least, some of the edges of the faces is at least 4 times the number of faces. Now this will double count some edges, right? I mean, an edge is going to be an edge like a border between 2 different faces. But if I just take each face and add up all of its edges, that'll be at least 4 times f, because each of those faces is defined by a cycle of length at least 4. But now let's get to the point that we've sort of double counted some edges. So we've double counted some edges, but we certainly haven't counted any edges more than once, right? An edge can be an edge for at most 2 faces. see, can be a boundary. For at most 2 faces. So that means each edge has been counted. You know, when we said let's sum the edges of the faces, each edge was counted at most 2 times. So that means that the sum of the edges of the faces if I've counted each edge at most twice, then that means that the sum of the edges of the faces can't be any more than twice the number of edges. So now let's look at these inequalities that we have, right? We've got that the sum of the edges of the faces, whatever that is, excuse me, the sum of the edges of the faces, whatever that is at least 4 times f, but at the same time, the sum of the edges of the faces is no more than 2 times e. So combining these inequalities, we get that 4f is less than or equal to 2 times e. Now we know the number of edges. The number of edges is 9, so that means 4f is less than or equal to 18. And now we've reached our contradiction because up here we said if it's planar, right, Euler's formula tells us that there must be 5 faces. But in this inequality, f cannot possibly be 5. So this contradicts Euler's formula. And that means that this graph, K33, is non-planar. Okay, so another result here in any connected planar graph with at least 3 vertices, it must be the case that 3v minus e is greater than or equal to 6. So we're going to do this in 2 pieces here. We're going to first consider the scenario, the possibility that G has no cycles. If G has no cycles, then the number of edges can't be any more than the number of vertices. So that means that E is less than or equal to V. And furthermore, since, let's see, there are at least 3 vertices by supposition here, since V is greater than or equal to 3, then 2V is greater than or equal to 6. Just multiplying both sides of that inequality by 2. And now I'm just going to subtract 6. So that means that 2v minus 6 is greater than or equal to 0. So we're going to use that in just a moment. But we know, so I'm going to go back to this right here. So we know that E is less than or equal to V. And I'm going to just rewrite this in a slightly different way. I'm going to say that it's less than or equal to V plus 0. And I'm introducing 0 here because I want to replace 0 with an expression equivalent to 0. Or that maintains the inequality at least. So I'm going to replace 0 with the expression 2v minus 6. 2v minus 6 is at least as big as 0. So if I replace 0 with something that is greater than or equal to it, I will preserve the sense of this inequality. So we have v plus 2v minus 6. And that means, now, if we simplify here, that the number of edges is less than or equal to 3b minus 6. And so that means that 3b minus 6 is greater than or equal to e. And if I subtract e and add 6 to both sides, we get 3b minus e greater than or equal to 6, which is what we wanted to show. So that's if our graph has no cycles in it. Now let's consider separately the possibility that G might have cycles. If G has cycles, that means that there are faces, right? So and we'll note that each face is bounded by at least 3 edges, right? It takes at least 3 edges to bound a face. Oops. And as we observed in the last result, each edge is a boundary for at most 2 faces. So that means that, you know, the sum of the edges of the faces is at least 3f, but it is at most 2 times the number of edges, so we get another inequality here. That means 3 times the number of faces is no more than 2 times the number of edges, right? In other words, we're saying at most the expression 3f counts each edge twice. So now we'll use Euler's formula. Which is v minus e plus f equals 2. I'm going to multiply both sides of this equation by 3, so that gives us 6 equals 3b minus 3e plus 3f. Now 3f is less than or equal to 2 times e, right? So I'm going to replace 3f with 2 times e, and when I do that, this equation is going to turn into now an inequality. So this whole expression is less than or equal to 3b minus 3e plus 2e. Right, I've replaced 3f with an expression that is less than, with an expression that is which is greater than or equal to the 3f. So that turns this the sense of this inequality. And this is equal to 3b minus 3e plus 2e is 3b minus e. So now let's look at this inequality that we have. On the one side, okay, we have 6. I maintain equality at first, then it switches to a less than or equal to, and then I maintain equality between these two. That means that overall I have an inequality that 6 is less than or equal to 3b minus e. Or in other words, 3b minus e is greater than or equal to 6, as desired. And there's that finishes up this result. The nice thing about this lemma is that if we have a graph that is connected, if it's planar, it must be the case that 3b minus e is greater than or equal to 6. We don't need to assume anything about the number of faces, just the number of vertices and edges. And so the way that this lemma is often used is it can be used to show that something is non-planar by using the contrapositive. So if we have a graph that is connected, if this inequality does not hold, then we can deduce that it is not planar. So, for example, K5 is non-planar. Well, we don't have to sit here and try to draw it or think about the, how many edges bound the face of a graph, of this K5 graph. We know that there are 5 vertices. The number of edges, let's see, any 2 vertices gives an edge, so then there are 5, choose 2 edges. That's equal to 10. So 3v minus e is 3 times 5 minus 10, which is 15 minus 10, or 5. And this is less than 6. And that means that K5 is non-planar. All right, so some more results. Every planar graph has to contain a vertex of degree 5 or less. If 2 connected graphs are homeomorphic, then they're either both planar or both non-planar. So a homeomorphism preserves this characteristic of being planar or non-planar. Any graph that is homeomorphic to either K33 or K5 is not planar. And here's a big one, Kurtosis Theorem. A graph is planar if and only if it does not contain a subgraph homeomorphic to either K33 or K5. So the graph itself doesn't have to be homeomorphic to K33 or K5, but if it just has a subgraph that is homeomorphic to either K33 or K5, we know that it is non-planar. Showing that a graph is planar can be pretty easy because all you do is just say, okay, I can draw it so the edges don't cross. For example, this graph here in 5-9, it's basically just 2 triangles that are overlaid on top of each other, but they don't have to be on top of each other, right? Like, that's not a vertex, right? That's just where 2 edges are crossing there. So we can just kind of slide one triangle out from underneath the other one. And there it is, a planar graph. Similarly here, we could show that this graph is planar. I'm going to start just by putting down the vertices. And let's see what we got here. I need to get from A to B. Maybe I'll do that. I need to get from A to E. So that takes care of those. I need to get from D to C and from D to E. And then I need to get from C to B, which I guess I'll just go this way. So it looks a little wonky, but look, we could do it. And as long as we could draw a graph so that the edges aren't crossing, and we know that it is planar. It's harder to show that a graph is non-planar because we could sit there and try to find a way to draw it so the edges don't cross, but maybe the reason we can't do it is just we haven't been clever enough or something, right? We could sit there for a long time. To show that it could never, that nobody could find a way to draw a graph so that the edges don't cross is more difficult. But Kurtosis Theorem helps, which means if we want to show that a graph is non-planar, one of the things we could do is just identify a subgraph and show that that subgraph is either homeomorphic to K33 or homeomorphic to K5. And that's what we're going to do in this last example. We're going to show that this graph, we call it the Peterson graph, we're going to show that it is not planar. So we will show that this graph has a subgraph that's homeomorphic to K33. The hard part is picking the right vertices. If we're showing that it's homeomorphic to K33, that means that we need to identify two sets of vertices, right? This is the complete bipartite graph, so I need to know what three vertices are going to be my top vertices, what three vertices will be on the bottom. So, and sometimes that just takes some guessing and checking and so I've got that hard part kind of done. We're going to pick the vertices E, F, and G to be on top, and J, A, and I to be on the bottom. So E, F, G, and then J, A, and I on the bottom. Okay, I'm going to zoom out a bit so that we can see both the given graph and the vertices that I drew here. Okay, so what edges do we have here? Certainly we've got this edge. I'm going to focus on I'll focus on the vertex A here. So I have an edge going from A to F and from A to E, and now I don't have an edge going directly from A to G, but I can get from A to G by going through vertex B. So what I'm going to do is draw this. I've got a pair of edges. It just has to go through vertex B. Okay, now if I look at vertex J, and that's right here on the inside, I have to get from J directly to E. I've got that edge, so I'm going to draw that in. What else do we have? I've got from J directly to G, so I could draw that in. And to get from J to F, now I can't get directly from J to F, but I can get there if I go through the vertex H. So I'm going to draw this edge. Say here's vertex H. So a pair of edges, right? From J to H and from H to F. Now let's look at vertex I. That's this vertex here in the middle. Let's see. I get from directly from I to G. So I'll draw that in. I can get directly from I to F. So I'll draw that in. And then how do I get from I to E? I can get from I to E if I go through vertex D. I'm going to draw the pair of edges from E to D and then from D to F. Okay, now you might look at this. So we're done drawing this subgraph. You might look at this and say, oh, but I've left off a bunch of edges, right? I mean, I left off this edge, I left off that edge, and that's fine. The Kurtosis theorem just says it has to have a subgraph that's homeomorphic. We don't have to include all edges or all vertices. It's just that we can only include edges and vertices that were there to begin with, and we have done that. Next, it's not that it had a subgraph that is K33, but this is homeomorphic. Remember homeomorphic, we make a homeomorphism to K33 if I turn, like I basically pick an edge and put down a vertex, so I turn one edge into two edges, right? Like if I look at this edge, you know, getting from J to F, in K33 there'd be no vertex H there, right? But that's fine. I took that edge, it's like I started with K33 and I took that edge from J to F and then split that edge into two by dropping down a vertex H on it. That's what it means to be a homeomorphism. So this is a subgraph. And it is homeomorphic to K33. And that means that by Kurtosis theorem, the Peterson graph is nonplanar. Okay, that finishes up this section.